Okay, good morning, everyone. We'll get started. Okay, so today we're going to be talking a little bit about coordinate systems, and you might think that sounds boring, but I can hopefully place it in the context of something that's quite interesting, which is antigenic cartography, or thinking about how viruses evolve. I gave around a couple of giant microbes. Where are they at the moment? Are they being passed around? Has someone stolen them? There's one. Where's the other one? Yeah, okay, good. Keep passing them around. What I want you guys to look at when you're passing those around is the little things that are dangling off them. These are the spike proteins in the context of coronavirus, okay? And all viruses will have certain types of antigens that will interact with our immune systems. And it's those antigens that our immune systems will recognize when either when we've had a prior infection and we've developed immunity, or we've had vaccination that targets those specific antigens. So what's all this got to do with coordinates? Well, we can think about how those antigens vary over time by thinking about a coordinate space that has many, many dimensions. Okay, so remember, this course is mainly about moving from things that are in one dimension to things that are in multiple dimensions. Okay, so this map up here on the top right is what's known as an antigenic map, or some antigenic cartography of the influenza virus. So seasonal flu viruses that are changing over years. And although there are actually 79 dimensions that these people who made this map looked at, they were able to essentially condense it down to 2 dimensions by doing projections. We'll talk a little bit about projections today, as well as that was in the pre-recorded lecture material. So this tells us something about how flu evolves over time. And we can do similar things with other viruses as well. So really the point of this lecture and problem class is to get you guys thinking about what happens in different coordinate systems and how that might relate to different biological problems. Okay, so can I have a show of hands who watched the pre-recorded lecture material? Good, what a class I've got. Okay, so I will just quickly skim through some of the material to make sure everyone's on the same page. If you have any questions, do please put up your hand. If I don't see you, then shout. So the pre-recorded lecture material was essentially talking about, okay, we're maybe familiar with coordinate systems in 2 dimensions. How do we take that to more than 2 dimensions? And in particular, what happens to relationships between distance, okay? And that becomes very important when we think about things like flu. If we're thinking about distance between flu viruses, that will tell us maybe something about how good a vaccine is against one compared to another, okay? So, okay, fairly simple. We can plot coordinates in 2 dimensions. There's a bit of notation here. These funny R's with the extra line in, you'll sometimes see in a textbook, they'll be in bold. Likewise with the Z's. The R's mean the real numbers. So that's anything that could be positive, 0, or negative. It could be fractions, it could be rational numbers, anything. When we have the 2 there, that means that we have 2 dimensions, okay? So we have, say, an X and a Y coordinate, 3, X, Y, Z, and so on. So this one at the top, P is in, that little almost E-like symbol means in. P is in the real numbers with dimension 2. So there's 2 real numbers there. Okay. So there was a little bit about right-handed coordinate systems. Don't worry about that stuff too much. It's just to tell you that there's a way to understand how we put our axes together. And although we tend to think about things in 2 dimensions or maybe 3 dimensions, mathematically, there's nothing special about that. And so we can generalize things to more dimensions. Okay, so this is Rn. We just have n real numbers now. And this is a point in Rn. So we can work out distances, fairly straightforward. Okay, so if we've got something in a 2-dimensional plane, say I want to work out the distance between me and Rowan. Rowan, you're the only person whose name I've learned so far. We just draw a straight line between us, measure the length of that line. That's the distance between us, right? And it'll be a different distance as we move around. If we're in 3 dimensions, say if I pick someone that's in one of the back rows up there, I can similarly do a distance calculation by just drawing a straight line to that person, drawing a straight line down to my height level, and then across, and then we've got a right-angled triangle. Okay, so just as we have a right-angled triangle here in 2 dimensions, we can do exactly the same in 3 dimensions here, and we just use Pythagoras again to work out that distance. And the same goes for any number of dimensions, okay? So it's very hard to think about what goes on in Rn if we have n different dimensions, whatever n happens to be, but the same formula applies. We work out the difference between each of the coordinates. We square them, sum them together, and then take the square root. Okay, so no matter how many dimensions in, the same rule applies, generalizes. Okay. I mentioned projection at the beginning briefly in the context of that artigenic, antigenic matrix even. And that is essentially just saying, okay, we're going to drop some of those coordinates. We're going to set them to 0, essentially. And we use this to, say, project down from a high number of dimensions into a lower number of dimensions if we don't really care about what those other dimensions say. There was something, just a quick announcement on the self-study problems. Thank you to someone who pointed that out the other day. There was a little mistake here in this DPR. It should have been 6 rather than 4. Okay. Before I move on to the problems today, are there any questions about any of the lecture material? Yes. Yeah. That's a very good question. I don't know the details of the paper. It's a long time since I read it myself, but essentially it's the ones that matter is the short answer to that. So you can, across a lot of those dimensions, they found that pretty much not much really changes, you know, or you can't get this like quite nice map that tells you something. So if I just quickly go back to the beginning, if you look at the dates on these next to these clusters, these are basically saying, okay, if we start off here in 1968, is this going to work? There we go. You move in the next few years onto 1972 and so on, and you go like this from cluster to cluster, right? And there's basically a movement in this downward direction. You don't really need to worry about what is the axes, you know, what down actually means here. But when they projected them down onto these 2 dimensions, they found that essentially there's a little bit of left and right movement, but you know, lots of movement in this one direction. So that one direction there is telling you that that is really the direction of selection by the immune system, by the immune profile in the population. That's what's really driving evolution in this case. So a lot of those other dimensions don't really matter as much, and this is saying that actually we can condense things down to just 1 or 2 dimensions. A very good question. Any other questions? Okay, let's go on to some problems. Let's see if this works. Good. Okay. So like I said the other day, what we're going to do is we're just going to work through problems in these classes. I'll work through some of them with you. Sometimes I'll get you to do them. What I want to think about here, first of all, is what space do each of these points belong to? So like I said the other day as well, I want you guys to engage. I want you to answer questions. So can anyone tell me what space this point here, 2 minus 1, belongs to? Hands up if anyone has the answer. Yeah, R2, yeah. So this is R2. It could also be in Z2 or even Z2 plus, because these are both integers. But R2 is fine. Okay, nice and straightforward. If A, B, C, and D are all real numbers, this is just going to be R4 because there's 4 of them. Pi, well, pi is just by itself. This is just in the real numbers. So if we want to have an example of points in different sets of spaces, P and R2, again, we've already had an R2 example, but another one, for example, 4.5 minus 3. Q in Z3 plus, so Z3, that's going to be the set of integers. We're going to have 3 of them because there's a 3 there. And then the plus here means the set of positive integers. Okay, so 1, 2, 3, for example. And then I don't know what's happened to the thing here. This should be R6, I think I had down. So in R6, again, we just need 6 numbers, whatever they happen to be. I'll let you guys fill that in. Very simple, right? These are just thinking, this is just get you thinking about what are different types of spaces. So let's think about this virus example. So like I said, the extent to which viruses can react with the immune system can allow us to talk about some sort of relationship between those viruses. How similar are they? And therefore, how can we develop vaccines that will target different types of flu viruses? This is essentially what public health officials and scientists do every year. The reason there's a new flu vaccine every year that you should get is because the flu virus evolves, okay? So we can think about the relationship between those strains by thinking about how those strains interact with the immune system. We call these interacting with different antisera. And so these numbers here for these different strains in this table represent the interaction between a particular strain and a particular antiserum. Okay, and these are just numbers, right? So we can think about each of these as being points in a system. Okay, so for example, if I put some brackets and commas here, we can think about this first row here, call it P1. And likewise, we can do this the second row, P2, and so on, P3, P4. These are just different points, okay? And each of these points, can anyone tell me what they belong to? Loudly? R3. Yep, so they're all real numbers. They're all in R3. In this case, what is N? If there are points in Rn, N is 3. Nice and simple, right? Now, I'm not going to go through this in class, but there is a website called math3d.org. Who's used math3d.org before? No one? One person, good. Okay, so you can use this to visualize some of the examples that we go through. So you can plot different points, you can rotate them around. This might help you think about the relationship between different points. And later on, when we get into things like vectors and surfaces as well, you can use Math3D to plot those things. Okay. So in the pre-recorded lecture, and just a moment ago, I talked about distances between points in a particular space. So how about working out what is the distance between a point and the origin? Well, we need to set one of the points to be whatever point is, one of the points to be the origin, work out the distance between those, and then we can see out of 2 points, which is closest to the origin is the one that has the closest distance. So have a little go at finding which of these points, questions 1 and 2, is closest to the origin. Remember, we're just going to create essentially a right angled triangle and then work out the length of that hypotenuse. Let's have a go at that. Also, this isn't a test. You can talk to each other. Whenever I walk around the class like this, please ask if you have any questions. Yeah. Okay, in the interest of time, guys, I'll work through these. So in the first one, the distance between P and 0, so P is 0 minus 2, 0. Well, I can work through the distance formula, but I can also just see that because this is 0 and this is 0, this is just going to be a straight horizontal line along the y-axis of length 2 in the negative direction. Okay, so I know that the distance straight away is going to be 2. For Q, it's a little bit more complicated. We need to work out the square root of 1 minus 0. So there's always going to be a minus 0 here, so I'm just going to leave the zeros out. So we're going to have 1 squared plus minus 1 squared plus minus 1 squared, which is square root of 3. 2 is equal to the square root of 4. So Q is close to the origin because the distance between Q and the origin is less than the distance between P and the origin. So Q is closer. In the second one, here we're in R4. So we're going to have 1 squared plus minus 1 squared plus 3 squared plus 3 squared, which is ultimately the square root of 20. And then for Q, we have 2 squared plus minus 2 squared plus 1 squared plus minus 3 squared, which is root 18. Unless I've made a mistake. So again, Q is closer to the origin. Can I have a show of hands who managed to get those? Great. Okay, good. So that's pretty straightforward. I'm going to leave this exercise either till the end if we've got time, or for you guys to do at home, because it's mainly a calculation question. But in problem 1.2, so that's where there was the table of the different strains of the anti-Sierra, we want to work out which of strain 2 or 3 is closest to strain 1. So how do we do that? Well, these are our different points. We want to work out whether this strain or this strain is closer to this strain. So just as we've taken the distance formula now between a particular point in the origin, now rather than the origin, we just substitute in whatever the other point is. Okay, so you need to work out the distance between strain 1 and 2 and strain 1 and 3 and see which of those is less. Okay, that's mainly a calculation question, so I will leave that as an exercise, or if we have time at the end. Okay, let's think about something slightly different here, thinking about how different sets of points might satisfy certain conditions. Okay, that might sound a little bit abstract, but sometimes we don't really just care about one particular point in a space. We might care about a selection of points. So if you think back, if you can visualize what that antigenic map looked like at the beginning, we had these clusters of viruses, right? So you might care about all of the viruses that are within a particular cluster, and therefore we might want to say, okay, how do we, if we're able to draw like a nice circle around them, or a sphere or something like that, then we can talk about the relationship between all of the strains that are within that particular set. Okay, so how do we do that? Well, here, this first part says, what is the set of points satisfying x minus y? So these are our points, minus the 0.23. Then here, this means the absolute value of that is equal to 2. So how do we work this out? Well, what does this mean? This means that we have x minus xy, sorry, minus 2, 3 is going to be equal to, since we're doing the absolute value here, we can take the distance. Okay, so this absolute value can also mean the distance here. So what is this? Well, this is the distance between the x coordinates. So we have x minus 2 all squared. We have y minus 3 all squared. And we know that from the right-hand side, this has to equal 2. So it's all values of x and y which satisfy this equation. So we could just square both sides here. So x minus 2 squared plus y minus 3 squared is equal to, I'm going to leave it as 2 squared here. Does anyone know what this is the equation of? This is saying that we're going to take all points in R2 that satisfy this equation, where if we take the difference between the x coordinate and 2 and square it, add it to the difference between the y coordinate and 3 and square it, is going to equal some constant. It turns out that's the equation of a circle. So if we have the equation of a circle centered, this is my x and y. If this is the point 2, 3, imagine that there's, if you're standing at the center of that circle and you've got a stick and you're going to turn around and say drag that stick in the sand, you're keeping the same distance as you go around. So that gives you a circle, in this case of radius 2. So it will touch one of the axes that's terribly drawn, but you get the idea. So that's all the points that are on that line, on that curve, and not the points in between. What do you think about this second one then? So what we've learned from above, it's going to be something a little bit similar, right? So now we're in R3, because we've got x, y, and z. So this inequality here is going to be some set of points. Have a chat with the person next to you, see if you can think about what that set of points is going to be. Okay, let's see what you guys think. Any ideas? Not from you three, because I've already spoken to you three. Any ideas on what this might be? What does inequality represent? Yes. Yes, the sphere, we're in R3, good. And what about that sphere? So the key thing here, what does this inequality mean? So in the first example, there was an inequality. So that meant the distance between all those points and the point that was centered, 2, 3, was exactly equal to 2. So when I span around in a circle and I was drawing a line in the sand, a circle in the sand, it was all of those points that were on that circle. If we've got this inequality less than or equal to 1, that means we want all the points that are within that sphere. Okay, so it's everything from me all the way out to the boundary of that sphere and including the edge of that sphere. Okay, so this is a sphere right here. So it's a sphere in R3. Where is it centered? So where's the central point of that sphere where I'm stood? It's not a trick question. You said that's right? Not on the Z point, no. Anyone else? Where is this centered? Yeah. Yeah. So it's a sphere in R3, centered at -1, 3, 0. And what's its radius? 1. Yeah. Key thing to remember here is that the reason I wrote this in the first example up here, let me just highlight it instead, as 2 squared, is because when we're writing the equation of a circle or a sphere, we have our x coordinates squared, our y coordinates squared, and we have our radius squared. Okay, remember that's the equation for a circle, the same applies for a sphere. So if this had been, say, 4, it would have been in R3, it would have been a sphere of radius 2. Okay, so we need to take the square root of that. So just be a little bit cautious because obviously 1 squared is 1. And it was less than or equal, so it's all points within. How about if it was just less than 1? What would that mean? Sorry, there's 2 of you. One, I'm going to go for you. So it's points within the sphere, right? So it's everything except for the shell of that sphere. And if it was, say, greater than 1, it would be everything outside that sphere. Okay, so we can use these relatively simple distance relationships to define sets of points within different spaces. Okay. Okay, let's go back to another biological example here. So Ronald Fisher in the 1930s measured different relationships and attributes between irises. And so we can write these down in a table. So we've got the different species here on the left-hand side, and then we've got different characteristics related to those flowers. So there's some lengths here, there's some widths here. We can think of each of these, again, as being points. This time, it's going to be a point in R4. So there's 4 dimensions here. And so suppose you go out into the field and you find an iris and you measure some characteristics about the iris, exactly the same characteristics we have here. Let's call this M. And we have these different measurements. Now, obviously, there's always variation within a population, right? Not every flower is identical to every other flower. But you know that on average, certain flowers within one species are going to be more similar, say, than other flowers in another species. And so by looking at the distance between these 2 things, we can try and say, okay, which of our example flower that we found, which one is it most likely to be by looking at how similar it is? So what I want you guys to do is to calculate the distance between this observed iris, this M, and the 3 above in the table, and work out which is the most similar. Can I just have a show of hands? Do people have calculators with them or not? You do have calculators. Okay, good. If you don't have calculators, then write down the equations for them at least. This kind of gets to the point of this line, okay? So M is just the point in this space. Every observation of a flower would represent a different point in this space that we can't do. Okay, let's see what you guys got. So remember, when we're working out the distance, we want to take each of the coordinates, and we need to make sure that we take the difference between the x's and difference between the y's, difference between the z's, and so on. We run out of letters, of course, but we need to make sure that we're always taking, because these are ordered numbers. We talked in a pre-recorded lecture, I believe, about n tuples. So these are numbers within these brackets that are ordered. Okay, so we can't switch the order around. The order matters. That means that, for example, you want to take the distance between M and Aristotozа. We need to look at the distance between 5.1 and 4.6. What's the difference between that? We square it, add it to, I'll just change the color here. The difference between these two, and square it. I'm going to run out of colors, I'm sure. Same with these. And then the same with these. We do that for each of these different points. So let's see what you guys got. Can anyone tell me what they've got for the distance between this first point P1, Aristotozа, and the observation M? Yep.
0.64.
Yep, 0.64. How about the second row? Yep. Yep, 0.32. And the last one, someone else? Yep. 0.15. Great. So we've gone out into the field, we've measured something, we've got some reference table. We've done this simple calculation, and based on our hypothesis that a flower that has distance, that has the smallest distance to one of these reference measurements means it's the most similar, what do we conclude? That our observation is most likely to be, which one's it most likely to be? The third one, right? That's because this value here is the smallest. So we'll talk a little bit about other ways in which we might define similarity between things when we talk about vectors on Monday. This is just one way of thinking about the similarity. Okay, we look at the distance in some space and we say, okay, the things that are closest together are most likely to be similar. That might not necessarily always be the best way. So that's why I said our hypothesis to start with. Okay, so we're making some assumptions about how the similarity between different species and within that species relate to one another. Okay, right. The last problem I'm going to go through today is thinking about projection, and I say problem, it's a very quick problem. Here we've got a person who's walking on a treadmill. It's going to be a similar question to this on one of the instructor questions, if I remember rightly. Incidentally, the first set of instructor questions has been released today. This is due next Friday on CrowdMark. Okay, so if anyone hasn't claimed their CrowdMark account yet, please do that. Also, whilst I'm thinking about another announcement, is that the online questions, they're already available. Can I just have a show of hands who's been able to access and look at the online questions? Okay, great. I know that Adam sent around an email about there being difficulties with some people connecting to that. Hopefully that will be resolved. Unfortunately, it was a problem on the publisher's end rather than ours. So we're a bit limited in what we can do to solve it, but hopefully it will get solved soon. Yeah. Yes. So guys, have a bit quiet, please. Thanks. So what we're doing here is we're saying the distance between, say, P1 and M is going to be the square root of 5.1 minus 4.6 squared plus the green one plus all of those, all of the other colors as well, and we take the square root, and we do that for all of them, yeah. Okay, so, sorry, not the other way around. as in 4.6 minus 5.1. It doesn't matter because we're squaring it. So that's fine, yeah. So sorry, I'll go back to this question just a second. So as Adam's email said that we're trying to sort out this problem at the moment with the online questions. Hopefully it will be resolved within the next week. But at the moment it's out of our hands. If you do, I'll send out an announcement, or Adam will send out an announcement if there's anything that you guys need to do, okay? Okay, so there was this question that I mentioned that is, there should be something on the instructor questions related to this, which is why I just wanted to mention it. I talked before about projections, okay, and this is just like what we do with the antigenic map. If we go down to this antigenic map here, we had 79 dimensions characterizing the relationship between all of these viruses and different antisera, and then we collapse it down by just dropping a lot of those, okay? And we could do the same with other types of data. So here we've got a person who's walking on a treadmill, and if we think about their center, it could be, say, their center of mass. As they walk, that center of mass is going to move around. And this trajectory here, this closed loop, is saying, okay, what is that center of mass? How is that moving on average as this person walks on this treadmill? Okay, so it's going to move left and right a bit. It's going to move up and down a bit. It's going to move back and forth a bit. Okay, but say we just care about what is their left-right movement. We don't care about what is their up-down movement. And likewise, if we care about their forward-backwards movement as well. So we don't care whether it's going up or down. We just care what's happening left or right and backwards and forwards. Well, in that case, we don't care about the Z coordinate here, right? We just drop that Z coordinate and we project all of those points down onto this XY plane. So this here, you think of this as being, say, the surface of a table or the floor. This will refer to as the XY plane. Sometimes it's written like this, sometimes it's written like this, XY plane. Okay, so when we take data like this and we project down, you can also think of it as, say, you've got some, in this case, like a rope that's moving around in all three dimensions, and you're going to shine a light on it from above, and you're shining that light down, and then the shadow is the projection. Also, you could shine from different sides, right? So maybe we don't want the XY plane, maybe we want the YZ plane. Suppose we care about, like Y is going to be, let's see, backward, left and right by the looks of this, I think. So suppose we don't care about the forwards backwards movement, we just care about left, right, and up and down. Then we could project onto a different plane, and we would get something that, say, if we wanted to project onto the XZ plane, so this one here, we would have something that looks, I guess, a bit like this, where we're now projecting in this direction. Okay, so we don't have to just shine that light from above, we could shine it from one of the sides as well. And all we're doing is we're saying, okay, we had an XYZ point each at XYZ. If we say drop our Z coordinates, we just end up with an X and a Y. So this, of course, means that you could have, if you've got a loop in 3 dimensions where it passes underneath itself and then you project down onto the floor, it's going to cross itself, it's going to intersect, even if it doesn't necessarily intersect in 3 dimensions. Okay. Right, with that, there's 5 minutes left. What I'll try to do in these problem classes, I'll try to finish a few minutes early if possible, because I know that not everyone will be able to make it to office hours. So in this time, you can either go back through what we've done today, you can come and ask me questions, or you can just leave. It's fine. Okay, I'll see you on Monday.